Today we're going to take a look at hex inverters and buffers, and there were 5 of them in the grab bag, and we're going to take a look at each of them. Now 2 of them right here in the middle, I couldn't actually get to work when I was messing around with them earlier, so I'm not sure if they're bad or if I'm just wiring them up wrong or if there's something on the data sheet that I'm missing. But we'll take a look at the other 3 and we'll put them up on the breadboard, and I think we'll run them through the oscilloscope and see if they can keep up as we change the frequency. So let's go ahead and jump in and take a look at their data sheets. The first hex inverter we're going to take a look at today is this Fairchild, and it's the 74F04 hex inverter, and it's a pretty straightforward basic model. It's got 6 independent gates, and you can see them on the circuit diagram right here. There's no clock line or output enable or anything like that. It's just data in, data out. And this is the circuit diagram for it. It's a little triangle with a little circle or an open circle on the output indicating that it's inverted. And that truth table is pretty straightforward. The input is low, the output is high, input is high, output is low. Now you might use a hex inverter if you need to switch a signal. So for example, if you're reading something in that's low and you need it to actually be high in that particular state, for example, to light up an LED. Maybe when your circuit goes low, you want to turn an LED on. So in that particular case, you could use a hex inverter in order to switch that in your circuit. So this one's pretty straightforward. Let's take a look at the next one. This is the data sheet for the second one. It's a hex inverter SN7405. Now, I did try to wire this one up before, and I wasn't able to get it to work. So I don't know if the IC I have is bad or if there's something about the data here that I just am not quite understanding. You'll see the chip pin layout is very similar to the previous one, input, output, and so on. Now this one doesn't really have anything special with it versus the one that we looked at before. The data sheet's just got a little bit more information. And here's the logic diagram, just as we saw in the previous one. And then here's that same truth table that's just inverting the output. We can take a quick look at the data sheet on this one, and we can see this is our chip. The normal supply voltage is going to be about 5 volts, so 3.75 up to 5 1/4. And then the input level needs to be a minimum of 2 volts in order to trigger the output. Otherwise, it's going to be high. And as you can see, the output current is about 16 milliamps. So it's really just meant to be a logic driver and not meant to control anything. You would need to use something like a transistor if you wanted to control a larger load or something like that. A single LED will be just fine. So here's that third hex inverter buffer, and this one I also couldn't get to work, and I'm not entirely sure why. This one had a little bit different on the specifications, but as you can see, the pinout is exactly the same. And here you can see the logic diagram is the same, and this one actually has the schematic of each of the buffers and the drivers if you wanted to look a little bit closer as to how they work. It's kind of fascinating. And then down here, there was just an interesting note. It said output voltage 30 volts, and so I don't know exactly what that meant since the supply voltage is 7. And that may have had something to do with why I couldn't get this particular one to work, or I might have just got a chip that's already been damaged. Here's that fourth chip, and this one's a little bit more complicated. It's the 74HC125. Now, you'll notice that it's called a quad 3-state non-inverting buffer. So what that means is quad, meaning there's 4 of them, which unlike the other ones that had 6. 3 states, which we'll talk about that in a minute, and non-inverting means that it doesn't actually invert the output. The ones that we looked at before were all inverting, so it would take a high and make it low. This one, a high, is going to remain high. Now you might be thinking, well, what good does it do to have a non-inverting buffer like that? Well, the reason this is the way it is that if it's sitting on a bus, and we talked about a computer bus in some of the previous videos, where the individual output can actually be 3 different states. So it can be high, it can be low, or it can be floating. And when it's floating, it has a high impedance, which means that it's not going to drag it down. So if you think about on a computer bus, if we were to say, okay, this output is low and it's going to go to ground, well, that's going to pull that entire bus to ground. And we definitely don't want that. But by having this 3-state, having a super high impedance state, means that we can have this on our circuit and then have the output disabled, and it won't indirectly affect that bus at all. So with that, we can look at the logic diagram, and you can see there's actually 3 pins associated with each of the 4 different buffers. And we've got a data in and a data out, and this time we have an output enable pin on each of them. Now that output enable pin is enabled active low. So when it's pulled down to ground, the output will now be available on the output or on the bus. But when it's pulled high, then the output will be a high impedance. So it's almost as if this is not hooked up to anything in that 3rd state. So because we have 3 states and because this is a non-inverting buffer, we've got an input of high, and then if the active output enable is low, which means we want it on, the output is high. If it's low and it's on, the output is low. And then the final state is that we don't care about what the input is, but if that output enable is high, then our impedance is also high and it won't pull that bus down. So that's where you see the 3 different states, the 3 different outputs, high, low, and high impedance. Here's the logic details of this buffer, and you can kind of see here's the output enable pin that we've got inverted, and then going to the out, and then here's our VCC. Here's our input, and it's being double inverted, and then going into these 2 AND gates. And it gets complicated. I'm not going to go through each of them. And then we've got 2 different MOSFETs over here controlling it, and then this is our particular output. So this allows us to be floating or high or low on our particular bus. So it's kind of neat. We might even take the multimeter and take a look at that in state when it's floating, so we can kind of see that high impedance. And lastly, we've got the CD74HCT245. Now this one is a 3-state non-inverting bus transmitter or receiver. And this one I just kind of threw in here because it kind of is a buffer, and it's kind of in alignment with the others and probably isn't worth doing a separate video on. But if you take a look at the pinout here, you might notice that it's completely different than the others. And that is because there's actually 8 inputs and 8 outputs. And we can control which direction the data is flowing because it can be used as bidirectional. So we can send data in or we can take data out based on the use of this direction pin here. In addition to that, it does have the same output enable pin that we saw on the previous chip. So it can sit on a bus, and then when the output is disabled, it'll also be high impedance and not bring that bus down. This is that functional diagram, and all the A0 through 7 can either be inputs or outputs, and then the B0 through B7 can also be inputs and outputs. Now, this direction pin will allow us to say which direction we're loading data. Are we loading data this direction, or are we loading data this direction? So a buffer like this could easily sit on the bus and then be used to talk back and forth. So for example, if we were to load something into a piece of memory, we would need to read it off the bus. And then if we were to read something out of memory and put it back on the bus, we would change that direction and we would go the other direction. And so that's how these buffers would work. And as you see, this is an 8-bit buffer. And here's the truth table. And this one's just functionally a lot different. It's non-inverting, but it's just talking about the output, enable pin, and then the direction, and then it's just giving you a wordage as to what direction it is. And then with that output enable high, then it's completely isolated and will create a high impedance line. And there's a quick look at their data sheets, and as you can see, even going through just the 5 different inverters and buffers, we've got quite a variation on functionality and different features on each. Some are completely independent, some would work more as part of a bus driver. So now with that, let's go ahead and head over and wire some of these up and take a look at them on the breadboard. The first one we're going to take a look at is this Fairchild Hex Inverter with its 6 independent gates. I've got everything wired up on the breadboard. It's a pretty straightforward circuit. I've got my chip, I've got my power, I've got my ground, I've got my 2 inputs, which are these switches here, and these are both going to be low right now. They're both pulled to ground using these green wires, which means my LEDs are on or high. And then if I press either of these, it takes that pin high, which makes my output low. And if I push both of them down, they both go low. So as you can see, they're completely independent of each other, and it works exactly as we were discussing. So it literally is just an inverter. So I got this wired up on the oscilloscope. I've got my little Arduino Nano project going here with my output signal. Now this is just a perfect square wave, and I do actually have the frequency set up correctly now, unlike in my previous video, so the knob actually matches up. And it matches up really, really well. So I've got this cranked all the way down to 60 Hertz. So the yellow line is going to be an input of 60 Hertz. The red line is going to be exactly half of that, which is our second LED. And that's going to be at 30 Hertz. And then I have the output of just one of them, which right now it is the first LED. So the yellow and the blue lines are the only two I'm actually going to use. And right now I am feeding in a 60 hertz on the yellow and a 30 hertz on the red. And then my output is going to be inverted because this is an inverted chip. So as you'll see on the oscilloscope, if we zoom in a little bit, we can see our input versus our output is inverted. And we can go ahead and just line those up, whoops, right on top of each other. And we can zoom in a little further and you can see they line up really, really, really well. Now that we've seen it down at around 60 hertz, let's go ahead and crank this up to maybe around 100 kilohertz. Now we have this at 100 kilohertz and we're still feeding in just the one yellow line and watching it on the blue line. And if we zoom in on the oscilloscope, we can see this is a perfect inverted sine. So this is looking really good at 100 hertz. We can go ahead and line those up as well. Whoops, wrong button. And you can see they line up really, really well on the input and the output. Okay, now we're at 5.3 megahertz. Let's zoom in a little bit. Ooh, that input's a little weak. Yeah, that is pretty weak at 5 megahertz. I did not check the data sheet to see how that should be behaving from a performance standpoint up at these high frequencies. But yeah, that's not a perfect line square wave. Let's crank that down just a little bit and see where it starts to look pretty good. Here we are at 1.4 megahertz, and that actually looks pretty good. That is a really nice overlap. Let's take that up just one little notch. There's 1.6 megahertz. There's 2 megahertz, 2.3 megahertz, 2.6. 3.2, even at 3.2 megahertz, that looks pretty good. 4 megahertz. So it really looks good right up until 5 megahertz. Right when it hits that 5 megahertz, it starts to drop quite a bit. But I think that looks pretty good either way. Now let's take a look at the quad 3-state non-inverting buffer. And again, this one has the 3 pins. It's got the data in, the data out, and the output enable. So let's take a look at that on the breadboard. Here we are. Now I've rewired this top switch because I wanted it to be active low. So right now it's been switched around. So when I press the button down, it's going to take it low as opposed to what it normally has been doing. This top switch is going to be my output enable, and the bottom switch is going to be my data in. Now remember, this is non-inverting. So right now, because my LED is on the bottom switch and it's low, if I take this right here and I turn it on, which drives that down to active low on my output, then my LED is off. My output is off. Now when I let up on this, this actually has a high impedance, and we'll take a look at that here on the multimeter in a second. Now to turn the LED on, what I'm going to want to do is I'm going to want to put my bottom switch down. So I've now turned this on, and now when I'm ready and I want my output to come on, I'll go ahead and take this to low as well. And the LED comes on. Again, non-inverting, so it's operating exactly as designed. Got the multimeter set up and my output is disabled right now, so you can see it's got a high impedance. It's just kind of bouncing all over the place. It doesn't have any connectivity whatsoever. So when I go ahead and press this down and I enable my output, you can see that drops to 0 or 1 millivolt anyway. And then when I let it off, it's going to go ahead and be a high impedance. Now, if I go ahead and turn my output on, but I don't have my output enabled, you'll see it has no impact. And then when I go ahead and enable my output, you'll see that goes ahead and jumps up to almost 5 volts. So when I say high impedance, that's what I'm referring to. When this circuit is, the output is enabled is off, then the output is high impedance and it doesn't drag the bus down. And here we have it on the oscilloscope. We've got it cranked all the way down to around 60 hertz on the yellow line. My red line is actually not hooked up to anything right now, and we're just looking at the output. Again, this is a non-inverting gate, so the input and the output match perfectly. Now, if you remember from a second ago, this one does have an output enable, which is this white line, which I currently have enabled. And what I want to do now is I want to make this output enable based on one of these other pins here. So I'm going to change it to this green one. And that's going to feed in a PWM signal with a different frequency. And that way we can just see a little bit of variation on the scope. So you can see it, and remember this is high impedance, so when it's in its off state, it's not going to be pulled directly to ground. So you'll see it kind of a little waffling around on the oscilloscope because of the high impedance, but then you can see where the two go high, or when the yellow line goes high and my output goes high, and then my output enable has just got that really short little tiny peak in there when it's also high. And then if I zoom out a little bit, we can see that's not going to be, well, that is actually pretty consistent pattern on what I've got in there. Now I just cranked it up to about 140 hertz on the input, and then I adjusted my output enable pin to have a little bit of a wider PWM circuit. So you can kind of see it's a little bit random going through there, but it's able to keep up obviously just fine at these low frequencies. Let's crank this way up. Here we have it at 100 kilohertz. We'll just zoom in a little bit and let's see what this looks like. All right, we're getting a lot of crossover on that because of that second frequency is pretty slow. Let's see if we can increase that a little bit. So our frequencies are off by too much to get a real good signal. So I'm going to go ahead and tie this output enable low again so that we can just see the full pattern on the screen. And then we can keep an eye on how well it does as we increase the frequency. So that's at 100 kilohertz. Let's go ahead and increase this up to the max. And this is 5.3 megahertz. Let's zoom in and see what it looks like. All right, that looks pretty good. Let's just move these over each other. All right, so this actually performed extremely well at 5 megahertz. Just given the fact that this is a newer chip versus the previous one we looked at, I'm not surprised that it's performing that well up at these frequencies. Now, I have a funny feeling that the last chip that we look at probably isn't going to fare quite as well at 5 megahertz. Let's scale this back just a little bit and see how it does. All right, let's go up from 2 megahertz. So here's 2 megahertz, here's 2.6 megahertz, 3.2, and then 5 megahertz, 5.3 megahertz. So that actually looks really, really, really good at 5 megahertz. And here's our last one wired up, and this is that 8-bit transmitter receiver with 3-state non-inverting. And again, this is the chip pin output, and we'll talk about these two pins that I've got circled here in a second. Now in the current state that I have this in, when I press either of these switches, the corresponding light comes on. So the switches are wired up on the A side, and then on the B side, I'm using as an output, and I have my 2 LEDs. And because it's non-inverting, when these go high, the output goes high. So that part is pretty straightforward, and we're bidirectional, but right now we're going that direction from A to B. And we're going A to B using this white wire right here. The yellow wire I just have as my output enabled, and I currently just have that hardwired to ground, so it's always on. But if I switch this wire around, this white wire around, and have that go ground instead of 5 volts, then my direction will go the other way, in which case I'll have to flip these around. So let me tweak that. Now I have my direction pin going to ground instead of 5 volts, so now my direction is going from B to A. So I've got my inputs over here on the B side, and I have my inputs or my outputs on the A side. So now when I press the first switch, the first light comes on, and the second one, the second LED comes on. Now just like before in their off state, which is going to be the output disabled, which is going to be high over here, there's no input and there's no output, and all lines are high impedance as we talked about before. So right now this chip is essentially out of circuit and isn't going to drag that bus line down or any other circuitry that might be plugged in. So now that we've seen that, let's go ahead and take this over to the oscilloscope and see what it looks like there as well. And we'll take a look at this last one. Not really expecting a whole lot on this one since it's a non-inverting buffer and our output should match our input. I have it cranked all the way down and you can probably see that LED blinking, although I think the shutter speed on the camera might be showing it less than what it really is. So this first LED is running currently at around 61 hertz and the second LED on the right is around 30 hertz. Let's go ahead and crank this all the way up to maybe 100,000. And there it is at 100,000 hertz. We can go ahead and zoom in a little bit. And in fact, we can go ahead and overlay those two, and you can see they line up absolutely perfectly. So no problems at all at 100,000 hertz. Let's go ahead and take it all the way up to 5 megahertz. All right, now we're at 5 megahertz. Let's just zoom in here. That looks really, really good. And we'll just go ahead and lay those over each other again. And we can zoom in and we can see, I mean, at this frequency, it's a You see it's trailing just a little bit on the output, but it looks pretty good. So that's all the way in at 10 or 50 nanoseconds per division. So it lines up really, really well. And that concludes our look at hex inverters and buffers. And we talked about a few other things along the way. So I hope you enjoyed that. I thought it was a lot of fun to put them up on the oscilloscope. I'm always amazed at what these chips were able to do, even way back into the 70s when a lot of them were originally manufactured.